Welcome back to the problem solving session for the thermodynamics course taken by Professor Anand. And in this week, again, we will keep on discussing about the entropy and the second law of thermodynamics. And if by now you would have attended the past two lectures by Professor Anand as well as the problem solving sessions by me in the past 2 weeks, you might have got a brief idea or a brief overview of what entropy truly is, at least in its very essence, what entropy does to a particular thermodynamic system, or why entropy is so crucial for determining the direction of heat transfer or energy transfer. Okay, so by now you might have got a bit of idea regarding that. Okay, and that's what my goal is for my end, for you to understand what entropy truly is, like why we are so concerned about the second law of thermodynamics. Okay, because if you see from equations, it's mostly in terms of inequality or some statements, whereas in the case of first law there's a very beautiful conservation law, very good equation, a balance which more or less gives us a very nice idea or a very analytical sense of equality that gives us an idea in a very proper robust sense of what the first law of thermodynamics really is. But second law of thermodynamics is mostly some inequalities, or say for example equations like this, or the closest inequality. So in essence it does not look very comfortable analytically, but you will see when you are a bit more clear on these concepts that why this second law is so crucial for this, not only from a perspective of this thermodynamics course, but from a perspective of science in general. Or you will understand how this second law of thermodynamics is basically a cornerstone for the sustenance of life in our planet. Okay, so I discussed it briefly in the last lecture, and also suggested you to watch a video by Veritasium on entropy. So I hope you would have watched it, but again, it's your choice completely. Okay, so in this week we'll continue to discuss about the second law of thermodynamics. We'll discuss about the gradation of energy, of why this work and heat are considered separately. We'll briefly discuss about it. Moreover, I have mentioned about these different gradation of energy while we're discussing about the first law of thermodynamics. So at that point of time I only gave you a statement. I also told you that it will make more sense when we discuss about the second law. So I hope now it will, if you are able to recall that, you will be able to appreciate that statement much more. And then we'll discuss about the different ways in which we can perceive entropy from different science branches. Okay, different branches of science. Then we'll briefly discuss about exergy or the availability, and then we look into the rate equation for entropy for both control mass and control volume. Okay, so that's the plan for today's discussions, and let me just reiterate again the agenda as all the weeks, as we do in all the lectures. That is, we'll briefly go through the concepts that were taken by Professor Anand in the lectures. Of course, I will not dive deep into each and every topic for saving time. Moreover, the contents of these weeks are a bit more concise compared to other weeks, so it will finish quickly. Moreover, the questions and answers are also, the question answer part is also quite brief, only 5 and 6 questions. So I think it will be done quickly only, but just saying to give you an idea. And then like if you have any doubt, you can stop me and I'll try to clarify. But of course, if I'm not able to do so, I'll suggest that you go back to the lectures by Professor Anand, or go to textbooks that were suggested by Professor Anand in the beginning of the course. Or of course you can put the queries and questions in discussion forum for this particular course. Okay, so with that brief overview, let us start today's discussion. So if you see this equation, I think by now you might be well aware about this equation. That is, for any system the change in the entropy is greater than or equal to del Q by T. Okay, and this equation, if you know, is not the closest inequality but a consequence of closest inequality, where closest inequality was given by cyclic integral of del Q by T is less than equal to 0. This was closest inequality. Okay, but this equation is related to it, but it's rather a consequence of closest inequality and not the closest inequality itself. Okay, so let's consider a particular case given by this diagram, that is the surrounding is at a temperature T naught, which is interacting with a system which is at a temperature T, where T naught is greater than T, and because the temperature of the surrounding is greater than the temperature of the system, there is a heat transfer from the surrounding to the system that is equal to del Q. Okay, yeah. Then from the first law we know that del Q system is equal to del Q surrounding equal to del Q, that is the heat given up by the surroundings is equal to the heat input to the system. Okay, so that's why del Q system is equal to del Q surrounding, that is equal to, say, a generic value of del Q. Now from this equation we can write del S system is greater than or equal to del Q by T. Okay, now del S surrounding would be minus del Q by T. Why T naught? Why? Because the surrounding is losing heat, that is equal to del Q at temperature T naught. So del S surrounding is minus del Q by T naught. So del S net, or the net change in the entropy for a system in a surrounding, would be given by del S system, ds system plus ds surrounding. Okay, I'm sorry, ds net is equal to ds system plus ds surrounding, or ds net is equal to del Q by T plus minus del Q by T naught. Now if we take this magnitude of del Q common, we will get ds net is equal to del Q times 1 by T minus 1 by T naught, and since this T naught is greater than T, that's why we will have this to be always be positive, and moreover, since del Q is the magnitude of the heat transfer, so this is also positive, and since both of them are positive, we will have this ds net to be greater than or equal to 0. Okay, that is the net change in the entropy for a system in a surrounding is greater than or equal to 0. That is something that we also got while we discussed about the net entropy change of the universe. Okay, now if this heat transfer between the system and a surrounding was done in isothermal way, then we would have got this, the temperature of the system and the temperature surrounding to be equal, it is T equal to T naught. Then we would have got ds net is equal to del Q 1 by T minus 1 by T naught, and since T is equal to T naught, this 1 by T minus 1 by T naught would cancel out each other, so it will be equal to 0, or ds net will be equal to 0, which is the net change in the entropy for the system and the surrounding, or the net change in the entropy of the universe, is equal to 0 for a reversible heat transfer. Okay, for this particular case. Okay, but from the principle of entropy generation, we know that the entropy of the universe keeps on increasing because of the very persistent nature of irreversibilities attached to most of the practical day-to-day life processes. Okay, so since most of the processes that we encounter in our daily life, almost all of them, they have an inherent irreversibility in them, say because of friction or temperature gradients or viscosity in fluid motion. So these kind of factors cause irreversibilities to be present in the system, which causes the entropy of the universe to increase. Okay, and that's in its very essence is the second law of thermodynamics, that because of these kind of irreversibilities, the entropy of the universe tends to increase continuously. Okay, there is no conservation of entropy. So I hope this is clear till now. Okay, so from this example we get some important conclusions, that is, heat transfer over a finite temperature gradient causes the entropy of the universe to increase. Okay, and as long as there is a temperature difference between the system and the surrounding, there is an increase in the entropy of the system, that is the increase in ds net. Okay, so from that we can write ds is equal to del Q by T, or ds is equal to del Q by T plus some positive quantity, that is ds gen, or the entropy generation, and this would be equal to 0 for a reversible process. Okay, so now let us just briefly take an example, or briefly go through this discussion in a schematic manner, that is heat transfer to a finite temperature difference. So whenever we have a heat transfer through a finite temperature difference, it causes irreversibilities, okay, or it generates entropy, okay. So consider these schematic diagrams. I'll zoom out a bit so that all the 4 diagrams are visible. I hope they are visible, okay. So this is a case where there is there are 2 thermal energy reservoirs at say temperature Th and Tl, where Th is greater than Tl. Okay, so we know that because of the spontaneous direction of heat transfer from this higher temperature to lower temperature, there will be a heat transfer or energy transfer from this higher thermal energy reservoir to a lower thermal energy reservoir, okay. And because of this direction of this spontaneous direction of heat transfer, we are able to obtain some kind of work if we put a Carnot engine or any direct heat engine between them. Because of this spontaneous direction of heat transfer, we are able to generate some kind of work, okay. So this difference in the temperature between the 2 thermal energy reservoirs acts as a potential of work to be produced, okay. So whenever there is a temperature gradient between 2 systems, there is a potential of generating some kind of work, which is exactly been shown here, okay. But again, even if there is but the key thing to take away is that, but even if there is no heat engine present in between, the direction of heat transfer will still remain the same, and still we will have a heat transfer, okay. So even without the presence of any heat engine or direct heat engine between these 2 thermal energy reservoirs, there will be a heat transfer because of the temperature gradient. And this heat transfer, this spontaneous heat transfer between the 2 temperature or between the 2 temperature limits or thermal energy reservoirs will generate entropy, okay. That is what exactly we saw in the previous example, that is in this example, okay. Let me go back. In the second case, in the second scenario, whereas in the second scenario we see that if we want to reverse the direction of heat transfer from this lower thermal energy reservoir to a higher thermal energy reservoir, we see that spontaneously this heat transfer won't occur. So we discussed it thoroughly when we discussed or introduced briefly about this second law of thermodynamics. So this heat transfer cannot occur spontaneously. We need some external agency to generate this kind of heat transfer from a lower thermal energy reservoir to a higher thermal energy reservoir, or simply from a lower temperature to a higher temperature. And we see that to achieve this, we need to use some kind of reverse heat engine or heat pump, as you can say, where it extracts some kind of work. In this case, we can extract some kind of work from the surrounding that will generate the required work to cause the heat transfer to occur from this lower temperature to higher temperature, okay. And again, you will see that this kind of interactions will also consume entropy, because it is demanding some kind of external agencies to reverse the direction of heat transfer itself, okay. So this will, it's in a sense it will require even more entropy, okay, compared to this spontaneous case. But the key thing to note is that even if there is no external agencies involved in this kind of heat transfer, it will still generate entropy because of the very presence of the temperature difference or temperature gradient, okay. So I hope this part is clear, like how the presence of temperature difference causes entropy generation, okay. And I think we discussed it very thoroughly in the previous lectures, that the only way we can achieve a reversible heat transfer if there is no temperature gradient. But we again know from the principles of heat transfer that for a heat transfer to occur, we need a temperature difference. But again, what to say, conversely, if you see, then again, this, if there is no temperature gradient, there won't be any heat transfer. But if there is a temperature gradient, and even after if there is a temperature gradient, that it will generate entropy, so it can be reversible heat transfer, okay. Now from the first law, I hope this part is clear. So now we will look into what is entropy, okay. So it may seem very vague for me to again reiterate what is entropy, because we have discussed it thoroughly again and again what entropy truly is, and we even expected different kind of definitions from different branches of science, okay. So I told that this Clausius statement and the Kelvin-Planck statement is a definition of second law thermodynamics from the perspective of classical thermodynamics, okay. So a different branch of thermodynamics or different way to approach this thermodynamics, say statistical thermodynamics, will have a different definition for entropy or the second law. Okay, but for better clarity, I think it's better for us to go through these other kind of statements as well. Okay, so from the first law we get that d, the change in energy of the system, is equal to del q minus del w. Okay, so there's a balance between the heat transfer and the work transfer, and this balance gives us one more thermodynamic property, that is the energy of the system. Okay, so it's basically the conservation of energy. From second law we get an equality, that is ds equal to del q reversible by t, but again this equality is very limited from the perspective that is only limited for reversible heat transfers. Okay, so in very essence we cannot say this is the second law, but we can say in general the change in entropy is given by ds is equal to greater than equal to del q by t. So this can be a mathematical definition for the second law. Okay, but I would say the second law is not only limited to this particular definition. Okay, that's what we need to understand. Then if we want to define entropy in terms of the very equation that is present in front of us, there is this one, we can say something like the ratio of heat transfer to the temperature at which it occurs. Okay, so this is a mathematical definition, or I would say defining this equation in terms of words, which will give us the definition of entropy in terms of the rate of change of or rate of heat transfer rate of heat transfer divided by the temperature at which the heat transfer occurs. Okay, that's one definition. Second way to look into it would be in terms of statistical thermodynamics. Okay, so there's again a different branch of science or different way to look into this thermodynamic processes. Okay, so in that case this statistical thermodynamics uses probability to define entropy. Okay, so they say that the net increase in entropy that occurs during an irreversible process can be associated with the change of state from a less probable state to a more probable state. Or in other words, if a system undergoes a process which causes the states of the particles in the system to go from a less probable state to a more probable state, then we can say that the entropy of the system has increased. Okay, so I won't dive deep into it because I myself, I can say frankly speaking, I'm not that thorough with this kind of perspectives of entropy from the statistical thermodynamics point of view. But if you're interested, of course, you can go through it from your own end. But I will say from my end that you won't be asked any kind of questions in your exams or assignments based on this the definition of entropy from statistical thermodynamics. Okay, so maybe you may be asked a definition type of questions, so that is clearly given here, but you won't be asked numerical questions that involves looking into entropy from the statistical thermodynamics point of view. Okay, so this is one thing that I can ensure. Okay, but still I think we can at least discuss the parts that were discussed by Professor Anand in the lectures in this problem solving session. Okay, we will discuss them, but it's not that important from the assignment point of view or the exam point of view. Okay, so now I hope this is clear, the definition, that is, if a system undergoes from a less probable state to a more probable state, we can say that the entropy of the system has increased. Okay, that's one way to look into it. So there is a mathematical way to quantify entropy from a statistical thermodynamics point of view. That is, S is equal to K times natural log of W, where K is the Boltzmann constant and W is the thermodynamic probability of that particular configuration of the system. Okay, so now Professor Anand gives an example of a chamber in which we divide the chamber through the help of a film, where one side of the chamber has gas and other side of the chamber is vacuum. Okay, so if this partition is removed, so what do you expect? So it's one of the other, say, standard examples basically is free expansion, because this gas is expanding against vacuum, so there is no resistance for during the expansion of this gas. Okay, so we can say that this gas is expanding freely, and basically this gives us this process is termed as free expansion. Okay, so so once the gas undergoes free expansion, the gas particles undergoes free expansion, the gas particles will get evenly distributed in the chamber. Okay, will get evenly distributed in this chamber. So these gas particles being evenly distributed in the chamber is a much more highly probable state than the gas molecules being concentrated at one side of the box. Okay, so I think you can also understand from an intuitive manner, like if say there was a scenario where the gas was initially, like even after the partition was removed, the high concentration of gas would be located at one part of the chamber. Okay, so if it's only after some certain time that the gas will start expanding and then achieve full or cover up the full chamber. Okay, after being advected to all the parts of the room. But the initial state of gas being located at only one side of the chamber, you can consider it to be very what to say, improbable state. That this is very rare that this kind of scenario may occur. That's why we can say that the probability of this gas being located at a particular end of the chamber is highly less probable compared to the case when these gas molecules are evenly distributed in the chamber. Okay, so that's a high probable state. That's why we can say that when the gas has evenly been distributed throughout the chamber, so that state is a more highly probable state. So the entropy of that particular state is higher than the scenario when the gas is only located at one particular end of the chamber. Okay, so that's something that you need to understand. So basically, or one other way to look into it is that uh, the initial condition when the gas is located at a particular end of the chamber has a much less entropy compared to the case when the gas has been evenly distributed in the chamber. Or you can say this expansion of the gas throughout the chamber when the partition was removed has caused the entropy of the system to increase. Okay, so initially the gas was located at a particular side of the chamber, which it had some particular configuration, but after the gas has been allowed to expand, it achieved a different configuration, which is a more highly probable configuration, and the randomness of this gas molecules has also increased because it is now covering a greater area and has, since it's allowed to expand, it has higher kinetic energy. So you can say the randomness in the location of the gas molecules has also increased. So you can say this in the degree of randomness in the system is increased. So in that sense also the entropy of the system is also increased. So, and if I am not wrong, this is the very definition that most of the students who are new to the course may recall, that the second law of thermodynamics states that the degree of randomness, or you can say the entropy, is a measure of the degree of randomness in the system, which is absolutely correct, but it's a very vague statement unless and until you are able to understand it through the basic concepts. Okay, so now after you are thorough with all the definition, the process inequality, the Kelvin-Planck statement, and once you've undergone all these steps, now you can clearly understand what that particular definition really means. Okay, so I hope this is clear till now, this example. And just saying again, this statistical thermodynamics point of view of entropy won't be asked in the exam. Of course, the definition might be asked, but numerical problems won't be asked. That's for sure. But still, if you have any doubt, you can just, I'll wait here for 1 minute. You can ask. Like, of course, I'll be also limited to the discussions taken by Professor Anand in the lectures. I cannot go beyond that. But still, if there's any doubt in the discussion that we had till now, you can stop me right now, or else we can proceed. So if there is no doubt, I think we can proceed further. Okay. So there are two statements that are written in blue color that I think is quite important from the conceptual point of view for this particular course. Okay. The first statement is that adding adding heat increases the number of equally likely configurations and thus the entropy of the system increases. Okay. Let us take this statement for as it is. Okay. So there are many key terms such as equally likely number of equally likely configurations. So what does it really mean? So it is something that I think for the current scope of the course we cannot go beyond this particular definition. So right now you can just take it for granted. You can take this statement for granted, but still let us try to understand what these two statements are trying to convey. Okay, rather than looking into the specifics of each and every word, let us try to look into like what is it trying to tell us. Okay, so the first thing is that adding heat increases the number of equally likely configurations and thus the entropy of the system increases. Okay, but addition of work does not have any effect on a number of equally likely configurations and hence there is no change in the entropy. Okay, so that's the second statement. Okay, so in it, the statement in their essence are trying to say that this adding heat increases the entropy of the system. Okay, if you just disregard this number of equally likely configuration, this part, because this will require a much more deeper understanding of statistical thermodynamics, but if you just focus on this adding heat and increase in entropy of the system, so you can understand that this adding heat, or in other words, this heat transfer causes the entropy of the system to increase. Okay, but it is mentioned, it also mentions that this adding work does not affect the entropy of the system. Okay, or work transfer does not cause any kind of change in the entropy of the system. Okay, so these two statements are very, very important from the course perspective. Okay, from the perspective of this particular course. Okay, so these statements in their
Sir,
oh sure.
here what we are saying, the addition of work does not have any effect on the configurations, since there is no change in entropy.
Yes.
But work PDV, when the work is being done on the system, the volume increases, so the entropy should increase, right? That is my question. Does not this does not change the entropy?
That's what I'm trying to mention. Okay, so if you if you look in that way, you may think the entropy will increase. Okay, but from the statistical thermodynamics point of view, the number of equally likely configurations of the system is not affected when the work is given as an input to the system. Okay, so now you cannot correlate this number of equally likely events and the expansion of the gas molecules in the system to be the same. Okay, so these are two different things, so that's why you cannot correlate between them. Okay, or I will try to give another definition. Maybe say if I go down, I actually written it, so let me try to state it in another way. Okay, so in another way, this addition of work changes all the quantum states of the system at the same time. Okay, so it does not cause any entropy change, but when heat is added, in other words, it causes a gradient of energy transfer. So there is a gradient in the energy of the quantum states when heat is added, and because of this gradient in the energy, this gradient in energy causes the entropy of the system to increase. Okay, so I hope this gives a bit idea. Like when work is added, it increases the energy of the quantum states altogether. Like the energy of the quantum states will all the quantum states will increase at a single time. Okay, when work is added, but when heat is added, some of the quantum states will the energy of some of the quantum states will increase at some time, and gradually the energy of the other quantum states will increase after some time. Okay, so this causes a gradation or gradient in the energy which causes the entropy change. Okay, so that's something that I was able to add from my end. There was not discussed in the lectures, but I hope this gives a brief idea. Okay, so is it fine, Lokesh?
It states that the energy states will have the change in energy. The atoms which are in the energy states, they will be having a gradient when heat is added.
Yes.
When work is done, there is no change.
Yeah,
This
there's no gradient in energy. Yes, all of them, the energy of the all quantum states will increase at a single time. That's why
okay,
there
sir.
is no change in the configuration of the state in when the work is added.
Yes, sir. Thank you. There are few doubts in this. Actually, sir, I have written GATE in this domain for 5 times. This is my sixth time I am going to write GATE in engineering sciences.
Okay.
Actually, this course helped me a lot, and thank you, sir. And sir will be taking any tutorial session, like this live session anyway. Sir will be taking.
I don't really know. Like, if it would have been done, it will be announced in the course website. But if you have any doubt, you can put the this thought in discussion forum. That would
Actually,
be also fine.
actually, I would like to thank everyone, sir, because actually this is a very great course. I don't know how sir got this idea, but very few topics are left. Except those topics, everything is the entire GATE syllabus for thermodynamics and engineering sciences covered.
Okay, that's
Excellent.
really good to hear. Okay,
Yes, sir. Really, it's a great step actually.
okay. Thank you, thank you so much. Yeah.
Thanks sir, for clearing these doubts. Also, will make yeah a great impact on GATE paper this time.
Okay, okay. Sure. All the best. All the very best.
Thanks. Sir.
Okay, sure. Okay, thank you again to Lokesh and all the students for making this session quite interactive. So let us. I hope this discussion made this topic a bit more clearer. Thanks to Lokesh again. So let us try to proceed further. Okay. So let me go back. Yeah. So I hope these two statements gives you a bit of idea like what I'm trying to convey. Okay. So that in one way you can say that in or very simple terms, adding heat increases the entropy. Adding work or any kind of work interaction does not affect the entropy of the system at all. Okay. So and this characteristic of heat and work will have a huge impact on how we treat this heat and work. Okay. And why they are treated differently at the first place. Okay. So we know that from the very first law, the energy can neither be created nor destroyed, but it can be transformed from one form to another. Okay. So and these two forms are heat and work. Okay. But the question arises, like how much of heat we can convert to work and how much of work we can convert back to heat. Okay. So because of these characteristics, okay, because of the fact that the heat increases the entropy or causes entropy change and work does not affect the entropy, because of these characteristics, what happens is that 100% of conversion of work to heat is possible. Okay, I'm not saying again that it's always the case, but it is possible. Okay, for example, in the case of electrical heater or friction generator, because of the rubbing of two surfaces, in those scenarios the work input is almost equal to the heat generated. Okay, of course if there are certain irreversibilities in the system that are unavoidable, it will affect the net heat transfer, or it will affect the net conversion of this mechanical work to heat, or mechanical work to electrical work, or whatever that is. But in general, if the irreversibilities are diminished to zero, in that scenario the 100% conversion of work to heat is possible, because of the very characteristic that the work itself does not cause any entropy change, or work does not generate any kind of entropy. That's the first thing. So any kind of entropy that would be generated would be because of the entropy generated in the system, or irreversibilities in the system, not because of the work transfer. Okay, that's the first thing to note down. But the second thing that is much more important is that this 100% conversion of heat to work is not possible. Okay, and this is primarily because of the nature of the heat transfer. So even if we are able to generate a system which has zero irreversibilities, say zero frictional loss, zero mechanical energy loss, or even say zero temperature gradient, so even if that's the case, then also because of the very fact that this heat transfer, as discussed by Lokesh and me as well, that this heat transfer causes an inherent increase in the entropy of the system. That's why this conversion of heat to work, this 100% conversion of heat to work is not possible at all. And this again is also a consequence of the second law of thermodynamics. Okay, because of this entropy generation, because of heat transfer, this 100% conversion between heat and work is not possible. Okay, heat to work is not possible. Okay, so if required, if you want from your end, of course, you can go deep into looking into it, like why this occurs. So the answer to it would be the statistical thermodynamics point of view of heat and work. Okay, so that discussion, uh, like uh, like unfortunately is not within the scope of this course, but for your interest you can always go to standard textbooks to understand it in a better way. But for the scope of this course, these definitions should suffice. But now you know why it is occurring. Okay, so at least you know why it is occurring. Okay, so that's what I wanted to convey. Okay, and because of these different characteristics of work and heat from the second law's perspective, that's why we were treating this work and heat transfer to be completely separate entities from the very beginning of the course. Okay, even though there was interchangeability between them, the units of energy are also the same. There is work and heat. The units of both of them are also the same, and in many cases, people may try to correlate them as the same thing. But from the perspective of thermodynamics, or as a thermodynamics student, now you know why we need to treat them differently. It's because of the gradation of the energy, and because of these characteristics, we say that work is a high grade energy, and heat is a low grade energy. Okay, so I hope this part is clear. So, let us try to proceed. Okay. So this part I've already discussed. Let me just reiterate again that addition of work changes all the quantum states of the system at the same time, thus not causing any entropy change. Okay. But
Sir, a small doubt. Small doubt. Why heat is called low grade energy? What's the main reason behind that?
low grade energy is primarily because, like, since we are not able to convert 100% of heat to work, that's why it is called a low grade energy. And but since we're able to convert 100% of work back to heat, if the irreversibilities can be diminished in the system, that's why it is called a high grade energy work. So is it clear?
Yes, sir, understood.
Okay, okay. No, it's of course it's not a very important thing to know, but some textbooks they strictly mention it as well, like the gradation of the energies, like why it is called. And now this is also this statement also, like I call work as a high grade energy because 100% conversion from work to it is possible. But if you look in deep into it, like now you may ask why 100% of conversion of work to heat is possible. Now if you look into that, you need to again go to the statistical thermodynamics point of view of this discussion. So which is, as I mentioned, currently not in the scope of this particular course, but if you want to dive deep, of course you can do that. But it's just a definition that I've stated here. Of course there would be some mathematical expressions, equations that would consolidate these concepts, but for this particular course we are not able to take that into the account. But you may look into it if you need. Okay.
By not the definitions, but this work high grade energy and heat low grade energy, they twist and turn and ask the same question again and again. Many times they have answered the same question.
Yeah, so yeah,
And
so I hope this removes the confusion. Okay, so
yes, sir,
yeah.
sir, I understood.
Okay, thank you. Yeah, so as I mentioning, since addition of work does changes all the quantum states of the system at the same time, does not cause any change in the entropy of the system. But addition of heat widens the energy spectrum by the fact that it causes uh, a gradient of energy between the quantum states. Like some quantum states will have certain a high energy, and some quantum states will have low energy. So there will be different ranges of energy energy states for these different quantum states. So since the range of energy at the quantum states are different when we supply heat, this causes an energy gradient which increases the entropy of the system. Okay. So it's very, what to say, I would say personally I'm not satisfied with these statements. I need more proofs for this to understand it completely. But I would also have to respect the timing for this particular time limit for this particular session, as well as the course perspective of this particular course. So that's why I think we cannot go beyond it. And okay, but for students who are interested, they can look into it if they want. So let's proceed. Now we look into the reversible adiabatic processes for an ideal gas. Okay, how to look into reversible adiabatic processes for an ideal gas. So if you recall, if I'm not wrong, there was a very popular equation when we say that for an adiabatic process, the PV relation between pressure and volume is given by PV gamma is equal to constant. Okay, so how it is achieved, that we will look into it through these definitions. Okay, now you will understand so why this relation is valid for ideal gases if the process is reversible and adiabatic. Okay, so let us look into the TdS relations. If you or the Gibbs relations, if you recall, TdS is equal to du plus pdv. Okay, so these relations are valid for any kind of processes because these are only correlating these thermodynamic properties rather than these path functions. Okay, so since they're only correlating point functions, so these equations are valid for any kind of processes. So any approximation that we take, we can take beyond this equation. Okay, like let us see how it can be done. So from this equation, TdS equal to du plus pdv, you will get ds is equal to du by t plus pdv by t. Okay, and all these properties, that is s, u, p and v, are the state properties. So v here is also small v, that is specific volume, u is the specific internal energy, and h is the specific enthalpy. Okay, and s is the specific entropy. Okay, so we have TdS equal to dh minus vdp, that it will be equal to ds is equal to dh by t minus v by t dp. Okay, now for reversible adiabatic process, this change in entropy ds is equal to 0, we've discussed in the previous lectures. So from that you will get du by t plus p by t dv equal to 0, or dh by t minus v by t dp equal to 0. Now for an ideal gas, we know that the change in internal energy is given by cv times dt. Okay, for an ideal gas. Now if you substitute this in equation number in this equation, we will get cv dt by t plus p by t dv equal to 0. Now for an ideal gas, we know that PV is equal to RT, is the ideal gas law, or P by T is equal to R by V, or we can write 0 is equal to CV dt by T plus R by V dV. Now for an ideal gas, we also know that CV can be written as the ratio of the specific heat, the specific gas constant divided by gamma minus 1, where gamma is the specific heat ratio. So from that, if we replace CV by R by gamma minus 1, so we will get 0 is equal to R by gamma minus 1 dt by t plus R by V dV. Or if you just multiply this equation by gamma minus 1 by R, you will get 0 is equal to dt by t plus gamma minus 1 dV by V. Now if you integrate this equation, you will get natural log of t plus gamma minus 1 times natural log of V is equal to some constant. Now since PV is equal to RT, we know that T is equal to PV by R. Okay, so actually you can write something like this would be natural log of T times V to the power gamma minus 1 is equal to C. Okay, now T is PV by R, so if we just take the antilog, we will get T times sorry, it should be V, it's not gamma, it's V to the power gamma minus 1 is equal to some natural log of C. Let us take it to be another constant, say C dash, or we can, to remove confusion, let us it be C dash and this will be C, where C is e to the power C dash. Okay, then since T is PV by R, so we will have PV by R dot V to the power gamma minus 1 equal to C, or PV to the power gamma is R times C. Let me take again this C1, this is C1, this is C1, RC1, or PV gamma is equal to C, RC1 is equal to C. Okay, so this is how you obtain the equation or the PV relation for an ideal gas for a reversible adiabatic process. Okay. Now let us look in the red equation for entropy. Okay, so this equation is simply something like, we have the equation that is ds is equal to del q by t plus del s gen. Okay, this is the equation that quantifies this entropy generation. If you divide it by dt, you will get this equation. Okay, you will get this. That is the basic rate of change, rate of generation of or rate of entropy change. I was saying in correctly, rate of entropy change. So unlike the, now you can see, now unlike the energy equation, if I stay, unlike the energy equation, here the temperature at which the heat transfer occurs also has to be considered. Okay, so this is the main difference between, I won't say main difference, one of the crucial differences between the rate of energy equation and the rate equation for entropy. So the energy equation was basically, you got dE by dt equal to q dot minus w dot. So here we do not basically consider the temperature at which the heat transfer is occurring, but in the case of entropy, the temperature at which the heat transfer occurs also has to be considered. Okay, or if you just consider it for control mass, of course this equation is also valid for control mass only. Sorry, this equation also valid for control mass only. That's why this equation is also valid for control mass. For control volume, is if you recall, there has to be certain modifications made, that we need to take into account the mass flow rate as well, which will like when we consider it for control volume. So this equation is valid for control mass. Okay, where there is no flow occurring in the system. So entropy change can also occur in scenarios where there is a flow, say a flow through a particular duct or a pipe. So in those kind of scenarios where we consider a control volume, where a specific location through which our analysis is done, so in that case the rate equation of entropy will also be changed. Okay, so consider this example. Again, this example was, I think, taken by Professor Anand in the lectures. So we will just go through it once so that the validity of this equation can be solidified. Okay, so a heater in a room takes in 1.65 kilowatt of electric power at steady state and transfer out heat. Okay, the temperature of the heater is 550 Kelvin. Find the rate at which total entropy generation. Okay, so from the first law, I think the key terms can be underlined. It is 1.65 kilowatt of electric power, then 550 is the temperature of the heater. We need to find the rate of entropy generation. Okay, so from the first law we get that dE by dt is equal to q dot minus w dot. Now for a steady state, the time dependency part will get cancelled out, or will be equal to 0. So we will get q dot is equal to w dot, or we can write q dot is equal to minus 1.65 kilowatt. Okay, because why minus 1.65? Because electric work is done on the heater, that's why Q would be equal to minus 1.65 kilowatt. Okay, now from the second law, the rate equation for the second law, we get that dscm by dt is equal to summation of 1 by t q dot plus s gen, or in steady state this part will also be equal to 0 because of the time dependency. Now, so we will get this s gen dot would be equal to minus the negative of this summation of 1 by t q dot, or now q dot is minus 1.65, so negative part will be cancelled out, so we will have 1650 divided with the temperature is, again, temperature in these scenarios will always have to be taken in the absolute temperature scale. So we will have temperature would be at 550 Kelvin. If we divide that, we will get S gen dot, or the rate of entropy generation, would be 3 watt per Kelvin. Okay, so we will see that in most of these examples, it would be a good practice to start with the first law to get an idea of the relation between the heat and work interaction, and then use those derived quantities to solve the rate of this rate equation for the second law, or the rate equation for entropy change. Okay, now again, so we have to, as I mentioned, modify the equation when we consider control volume, where flow processes are considered. So just go back. So let's scroll down a bit. So again, the detailed derivation of this equation, I think I'm not going to take, for the sake of saving time and for the sake of the time limit of this discussion. So I will not take that, or because this would have been done by Professor Anand thoroughly in the lectures. So if you want the detailed derivation, I would suggest that you go back to the lectures. And moreover, I have, if I'm not wrong, I have taken the detailed derivation of the similar rate equation for the energy change when we consider the steady energy equation. So we are following similar steps, but this time around we are not just considering the instead of energy, we are considering entropy. Okay, so following the similar idea, event schematic diagram will also give you a brief idea like what are the entities they need to consider. So following a similar idea, you can find the rate equation for the entropy as well. Okay, so the principle of this rate equation for the control volume remains the same. That is, the total rate of change would be equal to the net influx minus the net outflux plus the generation. So influx would be the net energy, net entropy at the inlet. Out would be the net entropy at the outlet, okay, or the net entropy going out of the system, and generation would be the net entropy generated within the system. Okay, so if you see, then the rate of change of entropy, it is given by dSCV by dt. Now the net entropy inlet to a system would be summation of mi dot times Si minus the net entropy out of the system, there would be summation m dot E Se plus the entropy generation. And now entropy can be generated by two ways. First would be the entropy generation because of the irreversibilities in the system, that is S gen dot, plus the net heat interaction. The net heat interaction will also generate the entropy, or would be a source of entropy generation in the system, so that can again affect the entropy. So this will again be the other term for the entropy generation. Okay, but I'm not saying that that is the entropy generation itself, but this is a source of entropy generation in the system. Okay, but as S-gen term, that's the more popular, also known as the entropy generation term in the equations, that is because of the irreversibilities are considered separately itself. Okay, and these kind of questions, like then where you will be asked to deal, you will be asked to deal with the entropy rate of entropy change equation. In those scenarios, mostly they ask you to find the net entropy generation. Okay, that is the S-gen term. Okay, so that's the basic pattern of most of these questions. Yeah. Yes.
Yes, sir. Small question. What's the main here also the same, that heat is the only thing which is generating entropy, or any other component may also be there for the generation of entropy?
Heat only, right? That's why I wrote in. I was going to tell that work has no contribution to a change in entropy, so work interaction is not considered. But in other case, in the energy transfer, in the steady energy equation, you saw that there was a W dot term, if you recall. Q dot plus M dot E equal to W dot plus M, Q dot plus Mi dot Ei equal to W dot plus Me dot EE. If you recall, there was work interaction as well in the energy equation, because work is a form of energy, one way or other is a form of energy, so we need to consider it when we consider the rate of change of energy. But in the case of entropy, since work interactions are not causing any change in entropy, so work interactions are not considered. So only heat interactions, see, heat interactions are causing the entropy change. This is the entropy change because of the entropy generation of the order irreversibilities in the system, and this is the entropy because of the heat interactions. Heat may go out of the system, heat may be in as an input of the system. This will again affect the entropy change. So the major question usually arises when for this kind of cases is to find the S-gen, because there is no specific equation to find S-gen. It's just a positive term that we add into the process inequality to get an idea of how this irreversibility generate entropy. So the questions will mostly be based on the fact that you will be given you will be able to evaluate these terms as well. This one you need to find S-gen. So that is the pattern for most of the questions, and it's a good doubt. So I think I was going to mention it, and since you pointed out already, I will just say it again, that since work has no contribution to the change in entropy, that's why you can see that there is no work related terms in this equation. In this as well as in this as well, there is no contribution of work. But in the energy equation, you can see there was a distinct contribution of work in the rate of change of energy. Okay. So now, if we consider entropy change for a steady adiabatic process, okay, steady state case and adiabatic process. So see, as I mentioned, this term is only because of the heat interaction. So if we consider an adiabatic case, this term will be equal to 0. Okay, and if you consider steady state, this term will also be equal to 0. And then if you consider only a single inlet and outlet, you will get something like SE plus SI plus SGen. Okay, or I think I should add intermediate step as well. So it will be something like SI dot minus SE dot, considering this mass to be multiplied with the specific entropy to give you a total entropy change rather than specific entropy change, plus SGen dot equal to 0. Or if you just disregard now, integrate with respect to time, or you just want to find the net change in the entropy rather than entropy rate of entropy change, you get something like SE would be equal to SI plus SGen, or basically you will get SE is greater than less sign. For irreversible processes, because there will be no entropy generation because of irreversibilities, we will get this SGen term. If I go back here, SGen term to be equal to 0, so you will get SC equal to SI. Okay. So for the last topic of today's discussion would be a brief introduction to exergy analysis. Again, exergy analysis is not treated, like I won't say in a very detailed manner in this course. We are just introducing briefly about this exergy analysis. Okay, so exergy can also be exergy is also known as availability, or the maximum possible work obtainable from a system with respect to a reference surrounding. Okay, so we will get to the definition, but let us look into it, like how we are able to quantify it. Okay, now if we consider this particular system, okay, the reservoir, one of the reservoir that is at a temperature T, and it's interacting with the environment which is a temperature of T naught. Okay, so we place a reversible heat engine within this temperature limits, because since there is a temperature difference between the reservoir and the environment, there is a potential to obtain work because of temperature gradient. Okay, so we are placing a heat engine between them to extract some kind of work, and since it's a reversible heat engine, we will get the reversible work. Okay, from the energy conservation or the first law, we get that W reversible is equal to Q minus Q naught. Okay, and since it is a reversible cycle, we the net change in the entropy for the entire cycle would be equal to 0. So delta S would be equal to 0 for the cycle, since it is a reversible cycle. Okay, because you know from the process singularity, del Q by T equal to 0 for a reversible process. It is less than equal to 0 for irreversible process. So we will get Q by T minus Q naught by T naught to be equal to 0, since it is a reversible heat engine. From this equation, you will get Q naught to be equal to Q times T naught by T. Now if you replace this Q naught in this first equation, you will get W reversible as Q times 1 minus T naught by T. Okay, and this entity, this reversible work phi, is also known as phi. This is equal to Q times 1 minus T naught by T, and this entity is known as exergy. This is the maximum possible work obtainable as the system interacts with the reference environment to achieve equilibrium. Okay, so now you can see that if T naught is lower, if the reference temperature is lower, then the work that can be obtained from the surrounding will also be greater. Okay, so if the reference temperature is lower, then the obtainable energy is high. Basically, like if the temperature difference between the reservoir and the environment is higher, you will be able to obtain more energy, because the highest possible temperature that can be obtained is limited because of our, say, energy limits. Like, say, if you are, say, using a thermal power plant, say burning coal and generating energy, so uh, because of and because of this, like since you're generating this heat at a very high pressure, because of these mechanical constraints to contain this high pressure steam, uh, the temperature, the highest possible temperature that you are able to reach by burning this coal is limited because of mechanical constraints. Okay, so more or less in many scenarios, this temperature of the reservoir or temperature at which you are able to extract heat is limited, but the environmental temperature or the surrounding temperature plays a crucial role on in terms of the availability of the work done. So if the surrounding at which you are rejecting the heat or you are interacting with is lower, or there is a vast gap or a considerable gap between the upper temperature limit and lower temperature limit, the available work or the maximum possible work that can be obtained in that particular scenario also increases. Okay, so in this example only, if say your T naught goes down, so T naught is, say T naught 2 is lower, it will be here something, so the area under the TS curve will be greater, so you will be able to obtain more work from the given heat engine. Okay, and it is why it is maximum, because it is a reversible work. So if you consider general case, if it is general work done, then of course there will be some irreversibilities that will affect this maximum available work, but we are defining exergy to be a way, in a way that it is the maximum possible work that can be obtained within the two temperature limits. Okay.
Sir, a small doubt.
Yeah.
How exergy is different from efficiency? Because the work reversible divided by heat, again it is giving the same efficiency equation.
Yeah, it is giving the same thing, but we are defining it in a way, we are defining it in a different way, right? We are not now considering something like the reversible by Q. We are defining it in a way that this entity is the maximum obtainable work from a given reference surrounding. So see, when we discuss about efficiency, it's solely based on the system. It's only depending on a system, like what's the temperature or what's the net heat input to the system and what's the net work output. So our main goal is to understand the maximum possible work output for a given heat input. But in this case, we are considering like what is the maximum possible work that can be obtained for the given environmental conditions. Okay, so this T naught is not a temperature at which you are, I would say, the lower temperature reservoir for a particular, what to say, your engine or something. So it's a surrounding temperature. Yeah, it's a surrounding temperature. Okay, so you can of course always argue, like if we just take this as a denominator, this gives us a Carnot efficiency, but the goal of these two arguments are completely different. So the first one is to understand how efficient your particular engine is, so your working device is into consideration. But in this case, you are considering like depending on the environmental conditions, what will be the maximum possible work that I can obtain. So that should also be a matrix for us to understand, like given that we are given the particular environmental scenarios, this is the maximum possible work that we will be able to obtain. So let us quantify it using something known as exergy. Now after I know that, then I can model my engines or any device that I'm able to create or make that will operate within these conditions, and then we will discuss about efficiency. But this is the maximum limit that I can obtain. So that's a way to look into it. Okay, so you can always argue in that way that this gives one way or another, this tells out our efficiency, but it's about what we're looking into. That's important.
Yeah. Yes, sir, I understood. This is not not for a particular device, but for the availability which we are having.
Yes, it's not for a particular device. It's discussing about the surrounding. Okay.
Yes, sir.
At which you can, yeah. Okay. Thank you. So as you can see, so now the Professor Anand also mentions about the idealized case for an exergy reference environment. Okay. So the idealized case for exergy reference environment would be large, uniform, simple, compressible system, and environment should be at rest. So these are the scenarios where we can obtain maximum exergy. Okay. So I think we can discuss this as well. let us just try to go through. Again, this is a generalized case. Say if your heat source in this case is obtained through a heat exchanger, which is generally the case. So in this case, the energy equation, similar diagram, so I am not reiterating it again. So we have the energy equation as the reversal work done as Q minus Q naught, and the entropy for a cycle would be equal to 0, because for a reversible cycle we know that the net change in entropy would also be equal to 0, because entropy in itself is a thermodynamic property. So we will have the net cyclic integral of del Q reversible by T for this particular cycle minus Q naught by T naught. So del Q reversible by T would be equal to Q naught by T naught from this equation. I'm sorry. Or if you just consider a net entropy change for this particular, for a particular step, okay, say entropy change for these two scenarios, okay, in that case you can write something like delta S dash to be equal to del Q reversible by T equal to Q naught by T naught, because this has to be equal, then only this condition is satisfied. Okay, so we can write, since this story equals, we can write Q naught by T naught is equal to delta S dash, or Q naught is equal to T naught times delta S dash. Then phi can be written as W reversible is equal to Q minus T naught times delta S dash. Okay, so this is just it's a generalized case compared to the previous one, where we just considered it to be where the heat transfer is achieved through uniform temperature. So heat transfer may not be uniform, it may not be obtained at uniform temperature. It may also be obtained, for example, through the case of a heat exchanger, where maybe the case would be a uniform heat flux or uniform. So in that case, in a generalized way, you can consider you can derive exergy to be in this manner as well. Okay, so you can see that in this case, the temperature at which the heat is received is not uniform, but rather we can use these kind of relations to find the availability or the exergy. Okay, so I hope, yeah, that's all for the theoretical discussion for today's part. So I think we can start the problem solving part. So let us look into it. I hope the questions are visible. Okay. So the first question is, I hope the questions are visible. Okay, so let us look into it. So which of the following statements is or are correct in the spirit of principle of increase of entropy? Okay, so there are 4 statements. For an isolated system, increase of entropy, principle of increase of entropy. Okay, for an isolated system undergoing any process, the change in entropy is always greater than or equal to 0. That's the first statement. Second is, for an isolated system, because of the presence of irreversibilities within it, the change in entropy is always greater than or equal to 0. For any process, the total change of entropy of a system together with the surroundings is always greater than or equal to 0. And option D is, for any process, the total change in entropy of a system is always greater than or equal to 0. Okay, so these are the 4 statements. I would suggest that you may just go through them thoroughly and just tell what are the correct answers. Okay, there might be multiple statements which are correct, so you may want to look into it. corresponds, then I think I can discuss it. Okay. So let us look at, okay, yeah.
Yes, sir. For any process, the total change in entropy together with its surroundings is always greater than or equal to zero,
Okay.
which is option C.
Hmm.
Uh, for, for an isolated system, because of the presence of no, it is not correct. Yeah. Option A, for an isolated system undergoing any process, the change in entropy is always greater than or equal to zero.
So that's also correct.
Yeah, that's what I think.
So B and D are incorrect according to you.
Yes, sir.
Okay. Why is D incorrect? No. Okay. It's fine. Like, yeah, it's fine. It's fine. Thank you. So yeah, it's correct. So option A and C are absolutely correct. Let me just state it. Like, for any process, total change in the entropy of the system along with its surrounding is greater than or equal to zero. It's basically the uh, what to say, the entropy generation, sorry, the rate of change in entropy change for universe. So you know that from a second law, the change in entropy of universe is always greater than or equal to zero. First is, for an isolated system undergoing any process, change in entropy is always greater than or equal to zero. Again, if we consider our universe itself to be a isolated system, I think I discussed that example when we discussed about this law. So in that essence as well, that for an isolated system can also be considered, the universe can also be considered as an isolated system. So the similar argument for option C can be made for option A, that since the only way, if there is no heat interaction as well, the presence of irreversibilities inside the isolated system, or the presence of the processes that occur inside the isolated system, may indeed increase the entropy of the system. So in that case, the entropy of the system will always be greater than or equal to zero. But in that way, if you just see, option B is also correct. Why? For an isolated system, because of presence of irreversibilities, they mentioned that there are irreversibilities in the system. So if there's irreversibilities in the isolated system, that will inherently cause an increase in entropy. So they are always greater than or equal to zero. Okay, or it's always greater than zero. So is it fine? B is also correct. Is it fine? Because for isolated system, since there is no to say heat interaction, so we know that irreversibilities will increase the entropy. That is basically the entropy generation term, right? But for an
Yes,
isolated
sir.
system, since there is no mass transfer or heat transfer, so the only way through which the entropy can be reduced or affected is if there is a heat interaction. Okay, say through volume flow rate, or say or through conduction itself. In that case,
Yes, sir.
if the heat is going out of the system, the entropy reduction because of the heat transfer may outweigh the entropy increase because of irreversibilities. In that case only, the entropy of that particular system may go down. But since it is an isolated system, so the entropy will always go up if there's irreversibilities. Okay, so option C is also correct. So with this argument, can you say why option D is incorrect? Option D is incorrect. Let me say it. Why it is incorrect?
And because of the heat transfer out of the system, it may
Yes.
decrease the entropy.
Yes, exactly. So they are not mentioning whether this is a closed system, open system. So they're just saying in the general sense, right? For any process. So total change in the entropy of the system only. They're not considering even the surrounding. So since they're only considering the system, the entropy of the system may go down if there is a heat transfer out of the system. So that's why this statement is incorrect. Okay.
Yes, sir.
So let us go to question number 2. Thank you. Let's go to question number 2. In a coordinate system where the natural log of natural log of p, ln natural log of p is the y coordinate, and h, enthalpy, is the x coordinate, the slope of the constant entropy line for an ideal gas is given by which of the following? Okay, so basically they're asking, like, if this is some kind of plot where ln p is the y axis and enthalpy is the x-axis, what will be the slope of a constant entropy line? Say this is a, for example, this is a constant entropy line, just saying, it may not be the case. What will be the slope, or what will be the expression of the slope of this particular line? So you are asked to find slope, it is equal to, say, ln p2 minus ln p1 divided by h2 minus h1. So this is the definition of a slope of a line, right? So what will be the slope? So one hint would be, since all of you are trying hard, so one hint would be to use the TDS relations. You may use TDS relations to obtain the slope. Specifically this one, TDS is equal to TH minus VDP. So I think this hint must suffice. So with this hint, say I will give you 4 minutes. I think that will be fine. 4 minutes to try to answer. If not, like if you are not able to do that, maybe we can look into the answer together and then we can proceed. So you can try that out. I'll give you 4 minutes. Second hint is constant entropy. So what would constant entropy, how would constant entropy affect this equation? You may try to look into that.
Sorry, is it V?
B. Are you saying this one?
V. Option
A.
A.
A. Okay. So let me just see. I think it's not.
Okay, sir. Let me recheck again because I have just solved it by observation. I need to check it with pen and paper. I'll check it.
Yeah, sure. Uh, one more minute. You can try it parallelly, no problem. But after that, maybe for other viewers, we can just look into the solution and then think we can do that. Okay. But it's great that everybody is trying, so it's good. Okay. So I think we can just try to look into the solution. course, thanks again, all of them, all of you who are trying. But just for the sake of saving time, since we have few more questions, I think we can proceed. Okay, I will just try to show the solution, but thanks again for trying. Okay, please don't mind. So if you look into it, yeah, so this is the question. Okay, so we have, as I mentioned, one hint was to use the TDS relations, TDS equal ds minus vdp. So for a constant entropy line, we'll have the change in entropy, that is ds, to be equal to 0. So we'll have dh is equal to vdp. Okay, so so if you look into this equation, then we can write something like if you divide this equation by p, okay, this entire equation by p, we will get something like dh by p is equal to v by p times dp. Okay, or ds by pv is equal to dp by p. Okay, now this equation, what we need to integrate it. Okay, so if you integrate this equation, you will get something like let me just show you something like dp by p is equal to dh by pv. Okay, so if you integrate it, you will get h2 minus h1 divided by pv is equal to ln p2 minus p1, or you can write 1 by pv to be equal to ln, sorry, p2 by p1. Divided by h2 minus h1. So this sorry, this gives you the slope of the line, that is equal to 1 by pv. Okay, so option C would be the correct answer. Okay. Is it clear? Okay, so let us try question number 3. So let me just say it. So question number 3 would be a bit lengthy, in a way that it requires us to go back to the steam tables and this thing. It's a good exercise, good question for like revisiting the concepts, but I think it may take a bit of a while. So nevertheless, let us just try to read through it once. Okay, we have steam enters a turbine at 3 megapascal and 400 degrees Celsius with a velocity of 180 meter per second. Saturated vapor at 100 degrees Celsius, okay, important, saturated vapor at 100 degrees Celsius exits with a velocity of 80 meter per second. Okay, at steady state, again important, the turbine develops work equal to 555 kilojoule per kg, and heat transfer between a turbine and its surrounding occurs at an average outer surface temperature of 333 Kelvin. The rate at which entropy is produced within the turbine per kg of steam is, okay, so we are again asked to find the rate of entropy generation, rate of entropy production. Okay, this is basically rate of entropy generation. Okay, so this question, I think I may just take it directly, because this will clear out many doubts. There are two more questions left that requires the similar analysis. So I think that for that case, I may take this example, because this will if done by the students right now or the participants right now, may take a long time, because it involves to go back to the steam tables and so on and so forth. So for the sake of saving time, what we can do is we can just try to solve this question. I will try to solve this question in the screen, and after that maybe the participants can try to solve the rest of the two questions. Okay, so they will be similar, but this problem will give a much more idea of what we are trying to achieve. Okay, so So I hope the question is visible. You may take a screenshot or a photo of it, then let us try to look into the solution. Okay. So yeah, this is the solution that we have. So from the question, since there is only a single inlet and outlet, so Mi would be equal to Me from mass conservation. Okay, so let us take a generic value of mass flow rate, that is say m dot. Okay, now the rate equation for entropy generation can be written as dSCV. Since it is a flow problem, the steam enters and exits. Okay, so it's a open system. Okay, so we have to solve this problem from the perspective of control volume approach. Okay, in that sense we need to use the equation for control volume. So the rate of entropy generation can be written as dSCV, or the rate of entropy equation. Rate equation for entropy can be written as dSCV by dt is equal to summation of q dot by t plus summation of mi dot si minus summation of me dot se plus s gen dot. Okay, and for steady state this will be equal to 0. So what we will see that you will be left with to find this term. Okay, so we can write something like minus s gen dot m, because mi and me are equal to m dot, in this equation. So we will get minus s gen dot divided by m dot is equal to summation of 1 by t q dot by m dot plus summation of si minus summation of se. And since there are only single inlet and outlet, so summation can also be neglected. Okay, so the key thing is to find the state of the steam. Okay, because the state of the steam will let us know about the entropy at the inlet, the entropy at the outlet, because this equation requires that we need to find the entropy value at the inlet and the exit. Okay, so that's why given the conditions of the steam, from that we need to find the entropy of the steam for a particular state. Okay, so for that, since we are dealing with steam, we need to use the steam tables, right? We cannot use ideal gas law because we cannot treat steam as ideal gas, so we need to take the aid of the steam tables. So since the saturation temperature at 3 megapascal is 233.9 degrees Celsius, I have just written it right away, but it's an extensive process. You need to look into the steam tables for it, but I have just directly written it. Okay, but it's a lengthy process. So at 3 megapascal, the saturation temperature for the steam is 223.9. So since the inlet temperature is 400 degrees Celsius, it will imply that the steam is at superheated state. Okay, so what we need to do, we need to look into the superheated steam table for the pressure of 3 megapascal and temperature of 400 degrees Celsius. And if you look into that, you will get the value of enthalpy as, you will see why we are taking the note of enthalpy as well. So we will see the enthalpy will be equal to 3231.7 kilojoule per kg, and the entropy at the inlet would be 6.923 kilojoule per kg Kelvin. Okay, similarly at the exit, since it is given that the steam is at saturated vapor, so it is at saturated state, so we can directly look into the saturated steam table for 100 degrees Celsius. So at 100 degrees Celsius, the enthalpy is 2675.6 kilojoule per kg. Okay, just give me 1 second. And the entropy is 7.3541 kilojoule per kg. Okay, kilojoule per kg Kelvin. Okay, so this is the value of enthalpy and entropy at the inlet and exit. Okay, so this will give us the value of these two in the rate equation for the entropy. But the other term that we need to evaluate is this term, q dot by m dot. Okay, T is also given, this 333 Kelvin, the average surface temperature, but we need to find q dot. Okay, and then how to find q dot? We need to take the aid of the steady flow energy equation, if you recall, because from the steady flow energy equation we will get something like q dot by m dot is equal to w dot by m dot plus h2 minus h1 plus v2 square minus v1 square by 2. The potential energy term can be neglected, so we are left with the kinetic energy term in the enthalpy change and the work done, because work done affects the net heat interaction or net energy interactions. So work done per unit mass or per unit kg is given as 555 kilojoules per kg. Okay, so all the units now must be consistent in terms of kilojoules. Now you see why we have taken the note of the values of enthalpy as well at the exit and inlet. So we substitute the value of H2 and H1 in this equation, and V2 and V1, which are also given in the equation, and just multiply it to the power 10 to minus 3 because we need to convert it into kilojoules. So if you do that, you will get q dot by m dot is equal to minus 14.1 kilojoule per kg. Now you've got all the terms, that is you got SI, SE and Q dot by M and the temperature as well. So if you substitute all of this in the first equation, there is this equation, you will get S gen by M dot to be equal to, because we are asked to find the entropy generation per unit kg or per unit mass, so we will get S gen by M dot to be minus 14.1 divided by 333 minus 6.923 plus 7.3541 to be equal to 0.4374 kilojoule per kg Kelvin. So that's how you find the entropy generation. So we will see this is the general trend, the general way of finding entropy generation, or dealing with these problems that have this rate equation for the entropy generation. Okay, so this is the general, I won't say the generic solution, but most of the questions will involve this kind of steps. Okay, so I hope this is clear. So can we proceed? Okay. So again, this is a very simple question. Maybe you can try it out, and then after I think we can take one more question, and then it will be alright for this session. Okay, so question number 4 is again very simple, fill in the blanks. The quantity of energy is always preserved during an actual process based on the dash, but the quality is bound to decrease. This is dictated by the dash. Moreover, the spontaneous processes can occur only in the direction of dash overall entropy or molecular disorder. Thus, the entire universe is getting more and more chaotic every day. Okay. So it's a very simple statement that encompasses both the first law and second law, but you need to fill in the blanks. Okay, so these are the options. I'll give you say 2 minutes. I think it's more than enough. You can tell me the answer. Okay, it's very simple.
Option yes.
Option A. Thank you so much. So the quantity of energy, let me just tick it. The quantity of energy is always preserved during an actual process based on the first law of thermodynamics. Okay, that's well understood. But the quality of energy is bound to decrease, that is dictated by the second law of thermodynamics, as I mentioned, whereby heat is a low grade energy and work is high grade energy. Okay, it is based on its second law, and this is dictated by moreover, the spontaneous process can occur only in direction of increasing overall entropy. Okay, so entropy will increase our molecular disorder, and thus okay, so I hope this is clear. So let us try question number 5. Okay, I think if you do question number 5, then question number 6. Okay, yeah.
But I have a small doubt, sir, here.
Yeah.
Actually, the spontaneity of the process is not dictated by the change in entropy. It is dictated by the negative increase in Gibbs free energy. But here the statement is like the increasing in entropy is giving the spontaneous process. Only that statement can occur only, the only is present. That's why I am having doubt.
But the Gibbs free energy, but no. But from the thermodynamics point of view, any spontaneous process can only occur in the direction of overall increase of entropy. That's also true, right? It cannot occur the other way around. Even if you consider Gibbs free energy, it cannot occur the other way around, right? You cannot have a spontaneous process that decreases the entropy. Is it?
Sir, like for example, I am currently not able to recall, but if we have some or the other element which is in gaseous state, but suddenly if we release it into the atmosphere, which is having the boiling point, which is lower than the our container, whenever it reaches to the atmosphere, it suddenly gets solidified. It is a spontaneous process where the molecular entropy is getting decreased. But even then, it is a spontaneous process. That's why.
Okay, but molecular entropy of what? Of the gas?
Yes, sir. The entropy of the system, whichever we are taking.
But what about the universe? What about the surrounding?
Yes.
Yeah.
Okay, sir.
Yeah.
I understood.
Yeah. Okay. So, yeah, thanks for that argument. That actually consolidates or clarifies that out even much more. Like even when you consider gives you energy, you need to satisfy the second or thermodynamics. Otherwise, it's not valid, right? So thanks for that doubt. It in fact clarifies the concepts even more. Okay, thank you for that. So now for the last question, you can try question number 5. I will give you say 5 minutes or 6 minutes, as much you can want. You can take time. So you can try question number 5. Okay. So question number 5 is, a room is maintained at 27 degrees Celsius while the surroundings is at 22 degrees Celsius. Okay. The temperatures of the inner and the outer surface of the wall, where the thermal conductivity of the wall is given by 0.71 watt per meter Kelvin, are measured to be 21 degrees Celsius and 6 degrees Celsius respectively. The heat flows steadily through the wall of 5 meter times 7 centimeter in cross section and 0.32 meter in thickness. Okay. Determine A, the rate of heat generation through the wall, and the rate of entropy generation in the wall. Okay. So this is the schematic diagram of the given problem. So there is heat transfer occurring. So you need to find the heat generation through the wall, heat transfer, net heat transfer through the wall, and the rate of entropy generation. Okay. Try it out. I will give you say 5 minutes, so you can try that out. Then we can maybe that will be all for today's discussions. So one hint would be to use the Fourier laws of heat conduction. If you if not recall, it would be Q dot would be equal to minus Ka delta T by delta L. Okay. So delta T is the temperature difference. Delta L is the thickness or distance between the temperature limits. Okay. So in this case it will be 0.32 meter. So with that idea, you may try to solve it out. You will get Q dot easily. First part will easily be solved. Second one is a bit tricky. Since there is no mention about the direction of heat transfer, so you can take the spontaneous direction of heat transfer. So since the room is at lower temperature, so a room inside room is a higher temperature, so you can consider heat transfer to occur from the room to the surrounding. Okay. So this should give you an idea. Q dot can be found out from this equation easily. In this equation, S gen you need to find. Okay. Since there is no flow occurring, if you recall, there is no flow of the system, so you can just consider it to be through a control system approach or control mass approach. So the governing equation for your entropy rate equation for entropy would be something like ds wall dt is equal to summation of q dot t plus s gen wall. you are asked to find Sgen. And since it's steady state, this would be equal to 0. In other words, S dot gen would be equal to minus Q dot by T. Okay. So once you find Q dot, just substitute it in this equation, and T is the it's not tricky actually. So you do take the temperatures carefully and the signs for Q dot carefully depending on the direction of this heat transfer. Since there is no mention of direction of heat transfer, so it should be spontaneous direction of heat transfer from higher temperature to lower temperature. It should be going out from the room. Okay. Okay, last one more minute, then I think that would be all. Okay. So yeah, I think we can look into the solution. But again, I appreciate all of you who are trying to solve. Because of the time limit, I think we can look into the solution. Sorry for that, but let us try to look into the solution. Okay. So I hope the schematic diagram as well as the question is clear. So just try to look into the solution. So I'm just showing the solution not because I'm not I'm sure that you, and not because that I think you will not be able to solve it. I'm just showing that so that the viewers who are going to watch the video may get an idea. Okay. So the rate of heat generation through the wall can be evaluated from the Fourier's law. Q dot would be minus Ka delta T by L. So K is the thermal conductivity, is 0.71 times area is 5 times 7 times 6 minus 21, or anything you can take, any direction you can take. I need the magnitude of Q dot. Okay. So from this you will get Q dot as 1164.84 watt. Okay. Now from the entropy balance, we get ds wall dt is equal to summation of Q dot T plus S gen wall. Now since in steady state, ds wall by dt would be equal to 0, so we'll get S gen wall to be minus summation of Q dot by T. So if you look into the diagram here in this equation, in this question, the inner wall you can see receives a heat flux of or heat of Q, and the outer wall rejects the heat of Q. Okay, so this direction of heat transfer will govern your this part. Okay, the sign for Q in this equation, and the respective temperatures as well. And temperatures you need to take in the absolute temperature scale. Okay, so in that sense, you will get minus summation of Q dot by T. Q dot is 1164. Just take the magnitude. Here you need to take the magnitude. So 1164.84 divided by 294. That is the 21 degrees Celsius at Kelvin scale. Minus, because the outer wall is losing heat, so it will be 1164.84 divided by 279. So it will be 0.213 watt per Kelvin. Okay. So I think this is clear. Okay. So okay.
Small thing. We are having the room temperature also. Don't we need to consider that component?
No, we are just considering wall in this case, right? The entire, if they ask, then you can consider, but they are only asking for wall.
Okay. We are taking the system as the wall.
Wall, only the wall, yes. Okay, so yeah, that's all then for today from my end, and let's meet next week for the final week for this course. Okay, so thank you again to all the students for making this session interactive. Okay, so let's all meet next week. Okay,
Sir, thank you so much.
thank you.
Only the Otto cycle, diesel cycle,
Yeah.
and other two components are being that specific humidity and relative humidity. Only these four topics are not covered for the entire GATE syllabus, which is having the 100 marks.
Yeah, this
Actually,
co- this course, I think, thank you Sampath, thank you so much. I think this course only has up till this vapor compression cycle basic, right? Three
yes, sir.
cycles. Yeah, there
This
other
is
auto
next.
cycle, rear cycle, you can, I think, refer textbooks. It's similar
Yes, sir.
only. Yeah.
They way, way more high advanced one are Rankin and Breton only. So others we can look into the textbooks.
Okay, okay then,
Okay.
thank you. Yeah, thank you so
Thank you,
much.
sir.
Yeah.
Thank you so much.